Okay, let's try and solve this now using Python. Now remember, what we're trying to do is we have our rod, which is centered at x equals 0, y equals 0, z equals 0, and extending it along the y-axis from minus L over 2 to plus L over 2. And we're going to divide it into little bits, little sheets if you like, each of thickness delta y. And for each of those sheets we can work out what the x, y and z components of the electric field are at some other point using this step equation down here. And what we're going to do is we're going to have a loop starting from one end, and what we'll do is we'll, for each little segment, work out the contribution to the electric field, the x, y and z components, and we'll add them all up. So we'll take the value from here, add it to the value from there, add it to the value from there, add them all together to work out the total electric field over here. Now I've already written a program to do this based on one of the programs we worked with earlier in the course. What I'm going to do is just talk through some of the changes I made to this program to make it different from the ones we've seen before. So many things are very similar. We're setting the constants. Here we're setting the measurement position. This is the position at which we're trying to work out what the electric field is. And then we pick the length step. We're going to step upwards in y about 0.01 at a time. So that's the thickness of all the little slices we're going to see over here. Now previously we would then set up an array in which we store all the numbers so that we can plot them afterwards. We don't need to do that here. We don't care about the contribution of one particular slice or another particular slice. All we care about is the final electric field at this location. So instead of summing a whole array, we're just going to set up some sums, x sum, y sum and z sum. Set them all to 0 to begin with, and as we go through the loop we're going to steadily add the contributions from each slice until by the time the loop is finished these variables will be full of the total x, y and z component of the electric field. Now we set up our loop. So we're starting at the bottom of the rod, which is y is minus a half L, and we're going to keep going until we get to the top, y equals plus a half L. So inside the loop we need to work out the electric field components due to that little particular slice at location y. So work out the displacement vector. So for y it's just y naught where we're measuring it minus y of the little slice. Then we use our step equation we worked out to calculate the x, y and z components of the electric field at this place. Once we've worked them out, we then add them to our sums. Print it out and increase y to the next step. And then we'll do that loop over and over again, each time working out the contribution to the total electric field from that little slice and moving the slice steadily up by dy each time. And the sums will get bigger and bigger and bigger until they come out with the total value, which I then print out here outside the loop. Okay, that's the theory. Let's see if it works. Well, it chugged through and it gave us electric field x component 358.21, which is what we got from Excel, looking pretty good. But the y component is not coming out 0. Z's coming out 0. We don't expect anything there because there's no trace in that direction. But why is y not coming out as 0? Well, if we look at our printouts here, we've got y, ex and ey. What you can see is the loop is stopping at 0.49, not at 0.5. Now why is that the case? It says while y less than or equal to 0.5, it should stop at 0.5. But these are floating point numbers, the decimals. So if in the computer, y won't be exactly 0.5 times L. It might be 0.4999999 or 0.501 or something like that. It's going to be some rounding error. Floating point numbers are never exactly the same in any computer program. So it sounds like y was actually very slightly more, and so it's actually stopped a bit early. And that's giving us our problem, because while it stops at 0.49 one side, it's starting at minus 0.5 the other side. So we're going to have an imbalance. There's just one step at one side that's not at the other side, and that's what's giving us a very small imbalance here. This is a fairly common sort of error you get in these sort of numerical steps. It doesn't really matter. If we made the time step smaller, this will tend to go away as well, but we might as well fix it. The way to fix it is you should never expect something to go up to equality. You always say, instead of saying, well, y is less than or equal to 0.5 times L, we'll give it a very small plus, 0.00001, say. That's very, very small. It's not going to affect how many steps it does, except that it means that when we get to 0.5L, a rounding error in our floating point number will no longer stop it. Okay, so let's run that. And indeed, you see it's now got all the way up to 0.5, and we now find that our y is very, very small. This is just a rounding error, indistinguishable from 0. Okay, so that all seems to be working. We end up with a sensible value for the electric field. Let's check and see whether our time step is small enough. If our time step is small enough, then shrinking the time step further shouldn't make much difference. So our time step is not a time step, a length step is 0.01. Let's make it 0.001. So now instead of slicing our rod into 100 slices, we're slicing it into 1,000, treating each one as a point and adding up their Coulomb's law electric field. If we run that now, instead of 358.24, it's come out as 358.21, which is a pretty small change, probably accurate enough for most purposes. If we make it 0.001, we can see what's going to happen. I'm going to stop printing out the whole numbers as it goes past by putting a comment hash in front there. That just turns it into a comment, so it doesn't do it, just to make it run faster. So now we can run it. And now instead of 358.2169, it's 358.2137. So now the difference is only 0.003. And if we keep making the time steps even smaller still, we can get it even more accurate as we like. It's not taking very long on the computer. So it seems to be working, and a time step of 0.01 or 0.001 seems to be accurate enough for most purposes.